Right, so I would like to go over a few basics in terms of graphing skills and how we can use a graph to represent the results of an experiment. So remember, when we're performing an experiment, we always start with a question. And this question can be phrased in this format. What is the effect of blank on blank? So remember, this first blank is describing your manipulated variable, so the thing that you're changing or the thing that you're testing. The result then, so what are you recording, is your responding variable. And when we record quantitative observations, so remember this is something that we measure that has a numerical value like distance or mass or time, height, something like that. And when we plot those points on a graph, always remember that your x-axis is where you put your manipulated variable and your y-axis is where you plot your responding variable. This is true for any type of graph in which you're recording results of an experiment. We always have our manipulated variable on the x-axis. Remember, manipulated variable is also referred to as your independent variable because it's not affected by anything else. This is what you are choosing to change or to manipulate. The responding then, often called the dependent variable, sorry, because it depends on what it is you're manipulating in your experiment will determine what sort of results you get. So let's take a look at an example. What is the effect of temperature on heart rate? So in this experiment, I want to see if temperature affects the human heart rate. So remember, what is the effect of manipulated on responding? So my manipulated variable then are going to be various temperatures. So perhaps I have people, a group of people that are exercising in 5 different rooms at 5 different temperatures, and as a result, I take their heart rate. My manipulated variable is the temperature. My responding variable then is the heart rate, which we record in beats per minute. A few things that are super important when it comes to graphing. One of those is that we need to correctly label our x and y axis. So the x-axis, that's the horizontal axis on the graph. So I'm just going to draw a little x here. And then the vertical side of the graph is my y-axis. So remember, the manipulated variable goes on our x-axis. So I'm going to label temperature, and we want to include those units, degrees Celsius. Actually, I'm just going to leave a little bit more space there. So I will just write that a little bit lower down here, the temperature in degrees Celsius, and then I label my y-axis with my responding variable, which is the heart rate in beats per minute. So we're going to write heart rate, and that's measured in BPM. Now, I have to choose a scale in order to label the axis. So what we mean by a scale is I have to find some way to include all of these numbers, and each square on the graph has to represent the same amount or the same number of degrees Celsius. So what I mean by that is if I choose this point here to be 0 degrees, then I may want to count every 2 squares to be 5 degrees since we're changing our temperature by 5 degrees each trial. So I would label this as 5, 10, 15, 20, and 25. The heart rate, on the other hand, we're going to have to choose a slightly different scale. So here, my numbers range from 58 to 75. So since I have nothing between 0 and 58, so my lowest value for heart rate on the table is 58 beats per minute. In this case, sometimes it helps to draw a scale where you put a little squiggly line here to show that you're skipping a few numbers. So instead of starting at 0 and counting 5, 10, 15, 20, 25, 30, because we have to get all the way up to 75 at least in order to include all those results. So what we can do then is draw our little squiggly line to show that we're going to be skipping some numbers. And then perhaps we want to count every 2 squares or every 4 squares to represent 10 beats per minute. So in this case, I'm going to start at 50. So I have my little squiggly line saying, okay, we're skipping up to 50, but from this point, every 4 squares is going to be 10 beats per minute. So the next one will be 60, and here 70. So if every 4 squares is 10 beats, then that means that every 2 squares is 5. So this would be 55, 65, 70, and 75. Now I can go ahead and plot these various points on my graph so that I can have a visual representation of the effect of temperature on heart rate. So at 5 degrees, my heart rate was 58. So I'm going to find 5 degrees on my x-axis, and then I'm going to trace that line up to 58 beats per minute. So if this is 55 right here, and this is 60 right here, then I'm going to estimate 58 to be about here. At 10 degrees, the heart rate is 60. So again, we find 10 degrees on our x and we trace with our pen up to 60 degrees. So here is 60 on this line. At 15 degrees, we have 64. So again, we trace up here. If this line is 65, then I'm going to estimate 64 to be about right there. At 20 degrees, the heart rate is up to 70, which would be right here. And then at 25 degrees, the heart rate is 75 beats per minute. So that would be right here. So we can see that there is indeed a relationship between temperature and heart rate. As we increase the temperature, we increase the heart rate. Often, people will include on their graph what's called a line of best fit. So this is where we draw a line. It's a straight line through our points, so we try to put it as close to each point as we can to show that it represents this pattern, that it's a steady increase. Okay, next example, I have what is the effect of water on plant growth? So again, I have my manipulated, which is the volume of water, and my plant growth is my responding variable, and I'm measuring that in centimeters. So our manipulated variable is always plotted on the x-axis, which is the one at the bottom, the horizontal. So I'm going to label this as volume of water, and I measure this in milliliters. And the y-axis then I'm going to label as the height of the plant, and this is in centimeters. Again, now we have to look at what would be the best scale. So it looks like I'm increasing the volume of water by 10 milliliters each time. So I would probably want to have my scale increasing by 10. So maybe every 2 squares is going to represent 10 mils. So we could label this 10, 20, 30, 40, 50, 60. And the height of the plant, we go from 8 to 15. So now I might want to choose a smaller scale since I have a much smaller range of numbers. So perhaps we want each square to represent 1 centimeter. So you would just want to double check that we have enough to go from 0 to 15. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Perfect, it just fits. So we're going to go up by 1 per square. And then we can choose we can start plotting our points on the graph. So just finish labeling my axes. 11, 12, 13, 14, and 15 centimeters. So the first plant receiving 10 milliliters of water had a height of 8 centimeters, so that would be here. Next one, 20 mils, we have a height of 10. 30 mils, our plant grows to 12 centimeters. 40 mils, we have a height of 13 centimeters. And then 50 mils, the height is 15 centimeters. So again, now we can connect those points with a line of best fit to show that the pattern does indeed relate water to plant growth. As we add more water, the plant experiences greater growth or becomes taller in centimeters.